Hi everyone. Today we're going to be working on savings and payout annuities. This is homework number 2. You should have already watched the video on homework 1, which involved simple and compound interest. And today we're going to talk about annuities. So last video, the conversation was about simple and compound interest, which was basically a sum of money that you were either borrowing or saving for, and that interest was either being applied one time or that interest was being applied compounded. Okay, now it wasn't money that you kept adding into. It was just a one-time pot of money, right? Either that you borrowed or you saved, and the interest was being applied in different ways, but again, it was one pot of money. What we're going to explore today is annuities, which is a type of situation that's different because, and this is going to feel a lot more natural because in most situations, when we want to save money, we don't actually have the ability to put all the money away at one time and then watch it grow, right? Like if our child is going away to college and we want to start saving now, for when they go away to college, we may not have all the money saved that we want to save to put into some sort of compounded account. What we're going to need to do is slowly put that money away month after month, right? And so as we put that money away month after month, if it's a savings annuity, there is hopefully some sort of interest that we're getting, and that interest grows. There's more money in there. And as there's more money in there, there's more interest in there, right? And then that compounded idea comes back into play. But the big difference is that instead of having all the money at once that I'm going to save and put it into some account to grow, it's something that I slowly add into, okay? So things like IRA accounts, 401ks, saving for the college. Those are all examples where I want to save for something big and I don't have that money all at once, but I want my money to grow in some sort of an account where I'm getting interest. And so I'm going to slowly add money into that. So the formula that we're going to be working with today, and there's going to be 2 versions, but really it's the same concept. But the first one we're going to talk about is a savings annuity. So a savings annuity, as we just mentioned, is a situation where I want to slowly put money away. And as I put that money away, whatever is sitting in there already is earning some kind of compounded interest. Okay? And so some of the letters in this formula may seem somewhat familiar, and then some of it is going to be a little bit new. So let's talk about that. So N, the first one, is going to be the number of years of investment. And what we mean by that is it could be months, could be days, but unless otherwise specified, it should be, in most cases, years, okay? So it's the number of years. Now, of course, as we said, that could change, but we will have to reflect that, and we'll talk more about that later. But for now, it's the number of years of the investment, okay? Okay, so the next thing that we're going to look at is P sub N, and that is going to be the amount in the account at the end of the investment period. And so what we mean by that is if I'm saving for my child's college in 20 years from now, the amount that's in there at the end of 20 years is going to be P sub n, okay? So it's the end number. It's what's in the account at the end of however much time that you're going to be saving this money for, okay? Then we have D. D is the amount of monthly deposit. Amount of monthly deposit. So if this is some sort of savings for the future, the amount that I put away every month, the amount that potentially comes out of my paycheck, the amount that I'm transferring from my bank account, whatever the amount that I'm putting in every month is going to be D, okay? R is my interest rate. So that's a thing we should be familiar with, interest rate. I forgot the E there, interest rate. And that is in, as we said before many times, in decimal form. Okay, so if the interest rate is 2%, we need to write that as 0.02, right? We're pretty familiar with that. You have to change it into a decimal form when it goes into the formula. Okay, and the last one, which we should also be familiar with from our conversations about compounded interest, is compounding, K. And that is going to be the number of compounds per year. All right? And as we mentioned before, compounding means if it's one time a year, K is once. If it's 2 times a year, semi-annually, that's twice. If it's quarterly, that's 4 times. So on and so forth. Okay. All right, let's look at this first example here because this will make a lot more sense after we actually try a problem. So you deposit $200 each month into an account earning 3% interest compounded monthly. How much will you have in the account in 30 years? So what we want to do is we want to look at this problem, analyze what they've given us, and figure out what is it they're asking me to solve for in this problem. So let's go through this word problem again now, and let's take out a highlighter or something and highlight all the important information. So you deposit $200 each month. So think about that to yourself for a second. What would the $200 deposited each month be? That would be my D, right? So we know that D equals $200 per month. Okay? Into an account earning 3% interest. So that's going to be my R. And we always write it as a decimal, right? So that's why we're writing 0.03. And then compounded monthly. And if it's compounded monthly, that is going to mean that every single month of the year, we are compounding. And that means if there's 12 months in a year, we are compounding 12 times, okay? How much will you have in the account in 30 years? So what they're giving you is the number of years that this is going to be going on for, right? That's my N. This is going to go on for 30 years. I'm saving for 30 years. And they want to know how much will you have? And so the thing that we don't know is the money in the account at the end. And if you remember our conversation not too long ago, that should be P sub n. So what we don't know is P sub n. That's what we're solving for. So let's look at the formula one more time. Here she is in all her glory. There is my savings annuity formula. So let's take that. I'm going to cheat here. I'm going to copy it because I think it's so beautiful. I'm just going to leave it as is. Okay, there it is. So we've got P sub n equals parentheses, and we have a D, and the D is going to be 200, parenthesis, 1 plus R over K, close parentheses, raised to n times k, and then minus 1, close parenthesis, all over. And then we have on the bottom there r over k. So that's 0.03 over 12. Okay, so let's have a talk here for a second about calculators. So if you're using the handheld scientific calculator, the good old TI-30X2S, this might be a little complicated to put into your calculator. Not that it isn't possible. So let me talk about putting it into there for a second, and then I'm going to show you my personal favorite way to do it. But first, let's do it with the calculator, okay? Just because we have to be able to do that, right? So how do we put this into our calculator? So step 1, you are going to put the top part in just as you see the first bit. You're going to have a parenthesis, 200, parenthesis, 1 plus. Now, personally, I always put fractions in a parenthesis like this. So I would do 0.03 slash 12 and then close that parenthesis. And then you're going to have another parenthesis because you got to close out this bigger bubble that we just made, right? Then you're going to hit the up arrow. And then again, because it's 2 numbers, I would put that in parentheses just to be safe and do 30 times 12, right? 30 times 12, close parenthesis. And then minus 1, and then close parenthesis, close parenthesis. So let's just verify that we made that. That makes sense. So we got parenthesis, 200, 2 parentheses, 1 plus that. All right. 200. And then, yeah, because we want this whole piece. See, basically, guys, this is where everybody gets confused. It's 200, but it's 200 times like this whole thing. You know what I mean? So like the 200 has to be outside, and then you need parentheses for in that part. So that's why I think that it gets a little confusing. All right, so I think this looks good. So this is how you should be typing this in your calculator. And then you need a slash for the bottom. And then you're going to want to put in parentheses 0.03 slash 12 and then close parentheses. And that should do the trick. So let me go ahead and put that in exactly as I wrote it, just to verify that I wrote it right for y'all. So parenthesis 200, parentheses, 1 plus, parentheses, and then 0.03 divided by 12, close, up arrow, parentheses, 30 times 12, close, minus 1, close, and then slash, and then 0.03 divided by 12. Okay, and we get, drum roll please, how much money will there be in the account at the end? It should be a whopping, hold on, let me move this over a little bit. A whopping $116,547.38. Okay, so now that I've shown you how to do this with the regular handheld trusty scientific, let me also show you what your homework calculator looks like. It looks a little bit different. It's actually the same as the Desmos Scientific. So let me go ahead and quickly pull that up for you. Desmos. I need my scientific. Hold on one second. Scientific. There we go. Okay, so how do we put this in our calculator? So you would do the exact same thing we did, only you don't have to write it in crazy calculator. You just kind of type it the way we wrote it out the first time. So if you hit the slash button or divide symbol, that will give you your fraction. And then parentheses 200, parentheses 1 plus, if you hit the 0.03, 0.03 divided by 12, and then you come outside of that parenthesis. You just have to hit that little right arrow, and then you hit the exponent, the a to the b, and this is the part where you have to be careful. When you hit that a to the b, it's making it an exponent, and you have to in there do 30 parentheses 12, so 30 times 12, okay? And then you come out of that exponent. So everybody watch what I'm doing here. You see I hit that right arrow. I'm no longer in the exponent, and then you do your -1. I see a lot of students who accidentally put the -1 in the exponent. Bad news bears, don't do that. Make sure you hit the right arrow and that it comes out of that exponent. Okay, so that's the top, and then on the bottom, just do your 0.03 divided by 12. There it is, and we get the same number we got before. So if you're doing this in your homework and you use the built-in scientific calculator, it looks like this. So this is how you could do it if you're using that calculator. Personally, for this unit, I am all about using the built-in calculator because it is nice. It makes computational errors a little bit less. But as I said before, you know, if you're using your handheld, that's going to work just as good. And there you go. That's how you should put it in. And do not, I'm going to put this in the notes, do not in any way, shape, or form put this in as pieces. What I mean by that, do not put in just the first bit, then do the next bit, then do the next bit. Put it in just like this. Well, you get the point. That was the answer, but just like this, okay? If you start putting it in as parts, okay, and rounding things that go on and on forever with decimals, your answer will now be slightly inaccurate. And when you go to put that in, it's going to send a red flag for your homework because they're going to be like, hey, that answer's slightly off. So what you want to do is make sure your answer is exact, and your answer is only going to be exact if you leave it all together like this until the end. Okay. All right. So I know that's annoying, but that is kind of a requirement. You do need to make sure your answers are exact until the end. Okay. How much money will you put into the account? So think about this. What you put into the account is your deposit, right? So if you put in $200 a month, which we already talked about, right? Putting in $200 a month, and you do this for 30 years, what you personally put into the account was $200 per month. So 200 times 12. And then you did that for how many years? 30 years. So we do 200 times 12 times 30. So if you put 200 times 12 times 30, right? When you put that into your calculator, you could go ahead and do that with me. 200 times 12 times 30, you are going to get 72,000. So you might be thinking to yourself, but wait, that's not this number, right? Like that's not the number we found. Of course it's not, because that number is the amount in your account that you put in plus the interest you got. So now the question is, how much interest will you earn? So what you earned, how much interest you earned, is the total in the account minus what you put into it, right? Because anything that you didn't put in was the interest. So all I have to do for total interest, and I'm going to write this out in words first, just so that everybody's with me, but you know, you get the point. The total interest is going to be the amount in the account at the end minus the amount in the account at the end minus the earned, not earned, the total amount in the account, and then minus the amount you deposited for 30 years. So what that ends up being is the amount in the account at the end. So that was the total amount, the 116. So the 116,547 and 38 cents. And from that, we're going to take away all that we put into it. What we put in for 30 years, month after month after month, which was the 72,000. If we subtract this, we are left with pure interest. And so that number is 44,547 and 38 cents. So that is the amount of interest earned, meaning I didn't put that in, I earned it by letting the bank borrow that money while it sat in there, okay? That's what that means. So, let's go ahead and try another problem. See if this is starting to click, okay? So, Jose has determined he needs to have $800,000 for retirement in 30 years. His account earns 6% interest. How much would you need to deposit into the account each month? So just like last time, let's go through this with a highlighter and let's talk about all the little baby pieces of this formula that they've given us and figure out what it is we're solving for. So Jose has determined he needs to have $800,000 for retirement in 30 years. So he needs to have. So what does that mean exactly? He needs to have. That's what we want in the account at the end. Does that make sense? That's the P sub N. So we know the amount in the account at the end needs to be $800,000. Capiche? Get it? 800,000 is what I want at the end. Okay? So, 800,000 for retirement in 30 years. So, what does that represent? That is my N. So, N equals 30 years. Okay? Next, his account earns 6% interest. That is my R. So 0.06 for R. Okay, next. How much would you need to deposit into the account each month? Well, they haven't specified the compounding. So if that's the case, then we're going to assume, well, you're putting money in every month. So that means we're just going to assume that they're compounding every month. Okay, so for this problem, K will be 12. And it says, how much would you need to deposit? So what is the only thing we don't have? Deposit. The thing that I don't know is the deposit. That's what we're solving for, okay? So what we're going to do, so let's write out the formula, get some practice in there. P sub N equals parentheses D, parentheses, 1 plus R over K, raised to the NK, and then minus 1. And that is all over R over K. Okay, so let's do this. So we've got 800,000 equals parentheses D, parentheses, and I left it as D because that's the thing we're solving for, right? 1 plus R over K raised to 30 times K, which is 12, minus 1 close parentheses, all over 0.06 my r over k my 12. Okay. What a hot mess, right? We got a lot of stuff going on here. Now, this is going to take a little bit of algebra for you to believe me, but we want to solve for D, and I'm going to rewrite this, and hopefully when I rewrite this, this is going to make a little more sense to you, and I'm going to be lazy because I don't want this video to be like an hour. So I'm going to rewrite this, and hopefully you believe me when I write it like this. Let me just do it real quick. Okay. Do you believe me when I tell you that these two lines are the same? I want you to look at this for a minute. Do you see that on the top, the numerator, I have D times all of this? Do you see that? I know this is an algebra move that might be a little confusing, but realistically, it's D times everything else. And the reason for that is because, as I mentioned before, this and this are all part of one parenthesis. And really, honestly, there should have actually been a second one, but at this point, who cares? We'll just take this one off. Okay, what I'm trying to say to you guys is D is being multiplied times all of the rest of that numerator. So why is that so important? Why do we care? Well, I want you to think about something for a second. If it's D times all of this, what is the opposite operation of multiply? The opposite of multiply is divide, right? So if I want to solve this for D, could I not literally take everything next to D, all of this, could I not take all of that and divide it to the other side and figure out what that is? Absolutely, sure you can. So here's what I'm going to do. I'm going to take that, and I'm literally going to, I'm going to make a little room here. I'm literally going to divide it to the other side. Now, is it going to be a little ugly looking at first because I've got fractions and fractions? Yes. But here's what I want you to take away is that now, because I've divided this to the other side, I'm left with D equals this entire thing. 800,000 divided by everything next to D. So that is what I'm left with. So if you do that, if you take the 800,000 and you divide all of that, you now could do several things. One, you can simplify this a little bit with some algebra, which I'll show you in a second. And option B, if you're using the Desmo Scientific Calculator, you could actually type it in exactly like this. So if you were to type this in exactly as is, and I'm going to actually side this one, so we'll put it right next to each other. Let me erase all what I had before, sorry. Okay, so I've got 800,000 over, and then on the bottom, I'm going to hit the fraction. Watch what I'm doing. I'm hitting the fraction again because it's 800,000 over that entire thing, okay? So it's going to be 800,000 over, and then now I'm going to put my my 1 plus, and then 0.06 over 12. And then I'm going to hit my right arrow so that I can get my exponent, 30 times 12. And then right arrow again to get out of the exponent, and then minus 1. And then underneath that, 0.06 divided by 12. So I want to just observe what's going on here. You've got 800,000 on the top. And then under it, you have a fraction. And that fraction is this. So this entire thing right here goes under the 800,000. Okay? You have to be very careful putting this in. I know it's annoying. It might take a little while for it to feel natural, but it will happen. You just have to practice. And our final answer is 7, and this is money, right? Because this is the deposit amount, 796.40. We're rounding it to 2 places because it's money. So what does that mean exactly? Every month for the next 30 years, Jose will have to put away $796.40 if he wants to have 800,000 in there at the end of 30 years, based on the interest rate we had, based on compounding per month. Now, let me show you one other method of doing this that doesn't involve using the Desmos Scientific, even though you can technically use this in your homework and stuff. If you want to use your handheld, you can use this too, okay? So let me go ahead and show that to you. So I'm going to come back here for a second and just give you one other method of figuring this out, okay? So let's back up. So as I said before, you could just take all the stuff to D and divide it to the other side under 800,000. We know that works. We know that we got the 796.40 when we did that. But if we wanted to do it with breaking down the algebra a little bit, you are going to rewrite that as 0.06 over 12 times the 800,000, right? We said we were going to do that to both sides. And then that's gone. So now I'm left with all of this, right? So that's here. And then if we take that and we divide everything else except the D, we're going to have 0.06 over 12 times 800,000. And then on the bottom, you should have parentheses, 1 plus 0.06 over 12, and then times 30 times 12, and then minus 1, and then close parentheses. Okay, I am 99.9% sure that that is written good now. Something in the way that I had it before, it must have just been like one parenthesis was being funky. All right, so let's try this again. So if we were to put this into our handheld scientific, we would be putting the 0.06 over 12 times the 800,000. Let me get my Desmos, but I'm going to do my best to write it. Hang on one second. Let's put the to the side. I'm going to do my best to write it the way we just did that. Let me erase this. Give me 1 second here. Okay. Parenthesis, 1 plus 0.06 over 12. And that is going to right arrow 1 time up 30 times 12. And then minus 1. Okay. Whew. 796.40. Oh my goodness. Okay. Sorry I made you guys go on a crazy goose chase there. And I'm going to just do one more thing before we go, even though you think I'm crazy at this point. I'm going to write it out the way you would put this into the handheld scientific, just to make sure that you have the ability to do this at home. So we've got parentheses 0.06 slash 12 close parentheses times 800,000. And we want to make sure that all of this goes in one bubble. So one more set of parentheses, because that's like the whole numerator, equals, and then we're going to put this parenthesis, 1 plus. Put that 06 over 12 in a parenthesis. And then close the whole thing up. 30 times 12. And, oh yeah, I'm sorry, I'm not doing calculator speak. We need to make sure, hang on a second, so that needs to go right here. Up arrow. So after you type the 06 over 12, then you need to close the parenthesis for the whole thing and then put it up 30 times 12 and then minus 1 close parentheses. Okay. All right, and then I don't know why I put that, but that should have been a slash. Okay, let me put this in one more time just to make sure it works for y'all, because I know that a lot of people, especially if you're in an asynchronous, it really is annoying when you're sitting at home and you're like, how do I put this in my calculator, right? So I just don't want to leave you uphill without being able to put this in your calculators. So I'm just typing it in right now. Give me one more second. So 800,000, close, divide. And then we have 1 plus 0.06 over 12. Close, up. 30 times 12, close, minus 1, close. Yay, it worked! Okay, so if you put this in exactly as I typed it into your scientific, you should get the answer. And I am very sorry I can't do better than that. I would have loved to just sit next to you and watch you type it in and tell you if I see anything, but I can't. So this is the next best thing. This is what you need to type in order to get the answer in your calculator. And as I said before, you can use the Desmo Scientific. It's the same thing as what's built into your homework. Okay, how much money will you put in the account? As we said before, what you put in is the deposit, okay? What Jose puts in as the deposit. That deposit is what we just calculated, the $796.40. And Jose does this every month, so times 12 monthly for 30 years. So that's what you're doing. You're going to multiply the deposit times 12, because that's how much in a year, and then times 30 years. So if you do that in the calculator, you should get 286,704. So what is that exactly? That is what Jose put in the account. Now, how much interest will you earn? Well, what you'll earn is the total amount in the account minus what you put into it. So the total amount in the account was 800,000, right? So 800,000, which is the total amount, minus the 286,704, which is what you put in. And what's going to be left from that is the interest earned. And so that number is 513,296. Good for Jose. Got a lot of interest there. That was really good. Okay. All right. The last question that we're going to talk about today is a different type of situation. So what we've talked about in the last couple of problems, I'm just going to pull back to the last one just so that you can see the writing. We were putting money away, right? And so we put that money away and then we have it for the day that we want it. So what happens on the day when you get that, when you reach that point, right? So like you're saving and saving and saving for retirement. What happens when you actually get to retirement, right? Like what happens when you actually reach that retirement? So what happens when you reach that retirement is that you start to take the money out, right? So you're retired now and you want to start taking out your money. And the question that you want to ask yourself is, do you want to take all the money out at once? And after some thought, the answer to that should be no. And the reason why you don't want to take it out all at once is because while you slowly take the money out, what's still happening to the rest of the money that's in the account? While you're sitting there taking out your little bit every month in retirement, the rest of the money sitting in that account is actually still earning some interest. So do you actually need all the money you need for the rest of your life on the day that you retire? No, you actually will continue to earn interest for the rest of your life while that retirement money is sitting in there. So now it will still, at some point, it's obviously still going to deplete, but you will earn more during retirement than what was in there when you retired. So that is what we call a payout annuity. While you slowly take the money out, the money that's still in there earns interest and still gets put a little bit back in while you're taking out. So let's talk about payout annuity formula for a moment. So the formula for the payout annuity has some similarities and it also has some differences. Notice that instead of P sub n, we're now talking about P sub 0, which you should remember because this is a variable that we've worked with before. It's the initial amount. And in this case, it's the initial amount in the account basically at the beginning. So on the day that you retire, that's what's in there, okay? And from that, we are going to take money out. And the number of years that the money still sits in there is still going to be n. It's going to be the number of years invested. So there's an n in there, and it still means the same thing. There's a d in here, and that still also means the same thing, except are you putting money in? The D, is it money you're putting in? No, it's money you're taking out. So now that D is actually a monthly payout instead of a payment, right? You're getting paid. It's a payout, right? It's not you putting money away. You're getting money. This is your retirement money that you're slowly getting out. And so the compounding for that could be quarterly, could be yearly, could be, whatever. So the monthly payment could also be that. You could be getting paid once every 3 months or 4 months or 5 months, whatever. So the amount of times you get paid per year, most typically for us, it would be monthly or bi-monthly, right? Because it's how we used to get our paychecks when we worked. But you get the point. So R is going to be the interest rate. Oh, and you know what? Let me just also add, could also be quarterly, yearly, etc. You get the point. It doesn't have to be a monthly payout. It's just the payout, whatever it is, for however many times you do it per year. Okay, and we said R is the interest rate, as always, in decimal form. And then K is going to be the number of compounds per year. Same as last time. So what's the same and what's different, right? Let's ask that question again, because if you know the difference between these two formulas, you'll never get confused. So what's different? Instead of amount in the account at the end, it's the amount in the account at the beginning, right? Because now it's kind of like, here's my big pot of money and I'm slowly taking it out. So we're starting with an initial amount, which is the amount in the account at the beginning, right? The initial amount. And then D is what you're taking out over and over again. And and that's pretty much the only difference in the variables. And then we're still working with R, we're still working with K, we're still working with N, and there are some differences in the formula, right? It looks a little different. The formula itself looks a little different. But other than that, not that much different, right? So how do you know when to use what? How do you know when I'm doing a payout and when I'm doing a savings? Okay, ask yourself the question, are you saving money or are you taking money out? Because that's the difference. Am I saving money every month or every year or however? Am I putting money away or am I going to be taking out that money? Or, as you'll see in your homework, there's a question in there where you're actually doing both, where they're like, okay, so you want to put away money now and then you want to take it out later, and it's kind of a doozy question, but we'll get there when we get there. All right, let's try this example. Based on the age when he plans to retire, his life expectancy, and other factors, Loren has determined that he will need to be able to take withdrawals from his payout annuity. All right, so we're using payout annuity. Boom, they've already told us that. He wants to be able to take them out for 30 years. So let's talk about this for a second. We're 30 years. That's N. After retirement. Considering inflation and other factors, he has determined that he will need to be able to withdraw $3,500 each month. Okay, we just got a lot of info right there. So withdraw, we're taking out. That's another ding, ding, ding. This is a payout annuity. He wants to withdraw $3,500 each month. So D is $3,500 each month. And obviously, because he's taking it out monthly, and I don't see any other information about compounding, we're going to go ahead with K being 12. And it says the interest rate is 7%, so R is 0.07. How much should he have in the account upon retirement to withdraw $3,500 each month for 30 years? So what is the question asking? It's saying, what does he need on the first day of retirement? What needs to be in there at the beginning so that he can withdraw $3,500 each month for 30 years? So the thing that we don't know is P sub 0. Does that make sense? I hope it does. So P sub 0 is the thing that I don't know. So the formula, so let's go back to the formula for a second. The formula was, I'm going to write it out for us. P sub 0 equals parentheses D, parentheses 1 minus, parentheses 1 plus R over K, close parentheses, negative NK, close, all over R over K. All right, so let's fill it all in. P sub 0, thing I don't know. D, 3,500. 1 minus, 1 plus, R, 07. K is 12. Negative N times K. Close. And this all goes over 0.07 over 12. Okay. How will we do this? Okay, hold on one sec. Sorry about that. Let me get this to the side so that we can observe together. Okay, so what are we going to do? So we're going to hit fraction and parentheses and 3,500, parentheses again, 1 minus, parentheses again, 1 plus, fraction, 0.07 goes over 12. I'm going to right click, because I want to get out of that bubble. I'm going to hit the A to the B, that up arrow, right? That's the exponent. Negative 30, parentheses times 12. And then I'm done with my top. Okay, on the bottom, I just need 0.07 divided by 12. All right, and there we have it. So the final answer is $526,076.49. $526,076.49. All right. As I always mention, enter this into the calculator all at once. Please do not do parts. Parts will lead to inaccurate answers. Okay, Next one, you have saved $500,000 for retirement. Your account earns 6% interest. How much will you be able to pull out each month if you want to be able to take withdrawals for 20 years? So, first question, is it a payout or a savings? And it says you have saved, and it wants to know how much will you be able to now pull out. So that tells me it's a payout, right? That's how we know that this is a payout. If you saw this mixed in with other questions, that's how you would know that. Now, aside from that, what are the pieces of the payout formula that you see in the word problem? You have $500,000. That means that's your initial. That's what you've got on day one of retirement. Your account earns 6% interest. That's my R, 0.06. How much will you be able to pull out each month? So we're pulling money out each month. And so that's going to be my K because they haven't said otherwise, right? If you want to be able to take withdrawals for 20 years, that's going to be my N. So how much will you be able to pull out each month? So what is the thing that we don't know? We don't know how much we're going to take out every month. So what we don't know is the deposit, aka the withdrawal amount. So one more time, let's write out the formula. You've got P sub 0 P sub 0 equals parentheses D, you get the point. So there's the formula. So let's plug in the things that we know. We know the initial. I'm writing out my stuff here. We've got R, which is 0.06. We know K, which is 12. We know N, which is 20. So negative 20 times K. And then close, and then that's all over 0.06 divided by 12. Okay, so just like our conversation with the last example where we solved for D is being multiplied to all of this. D is being multiplied to all of that. So if I want to get D by itself, I can literally take all of that and divide it to the other side. If I do that, D will now be by itself. So I can now rewrite this. Give me 1 second here. I'm going to just make this a little smaller because I'm running out of room. Okay, so I'm going to take my 500,000. I'm going to rewrite that first. 500,000. And you know what? I'm actually going to copy this because that's the size of it. And I'm going to divide everything except this D. And I'm going to write the whole thing, so just give me 1 sec to clean it all up. And then it's 500 over and then that bottom bit. So here's what happened. I literally took all of this, and if you don't believe me, pause the video and watch what I did. I took all of this. I took everything here, okay? I took all of that, and I divided it to the other side. So now all of that is sitting under the 500,000, okay? So this is the part where we can just Now go to our calculators. And what we want to type this time is 500,000. That's the top. And then underneath that, I'm going to hit the fraction button again because there's going to be a fraction on the bottom there, right? And then 1 minus, parenthesis, 1 plus, and then 0.06 divided by 12. I'm going to hit the right arrow to get out of that, and I'm going to hit the up arrow, the A to the B button, negative 20 times 12, and then I'm all done there. And then 0.06 divided by 12 on the bottom of that. So my final answer is 3,582. Oops, 582 and 16 cents. We always round money to two places, right? So what does this mean? This means that if we've got 500,000 sitting in the bank and we want to take out money every month for the next 20 years, that's how much you can take out per month. That's what we just figured out. So how much total money, so now let's answer the side questions here. How much total money will you withdraw in the account over 20 years? So this is the monthly amount we're taking out. We just figured that out. So if we take that number, the amount that we're taking out every month, and we multiply it times 12 per year, 12 months in a year, times 20 years, right? So this is the monthly D, and then multiplying it times 12 months in a year times 20 years, that is going to equal $859,717.27. So how much money will you withdraw? Now, back to our conversation real fast about not having all the money you need on the day that you retire. So if you follow this problem, how much did we have on the first day of retirement? 500, right? 500,000. But over the course of 20 years, 859,000 came out. Oh my goodness. That's way more than was in there on the day that we retired, right? So how much of that was interest? Well, to figure that out, we want to take the total amount withdrawn, which in this case is the 859, right? This is the amount that was taken out over 20 years. And we want to subtract from that the amount that was in there the day that we retired, right? And I'm actually going to rewrite that. Initial amount. Right? So the initial amount is what was in there at the beginning, which was the 500,000. So if you take what you pulled out minus what was in there in the beginning, that's how much that was earned through interest. So that means $359,717.59 was earned through interest. Wow. Like, talk about how awesome is that. So all of that money was not money you saved for retirement. That is money you earned on top of the money that was in there on the day that you retired. So that is pretty cool. And yeah, so that's just something to think about also. All right. Next question. A state lotto has a prize that pays off $1,600 each week for 35 years. Find the total value of the prize. Okay. So that's a pretty easy thing to figure out. The total value of the prize is the amount you get, $1,600, right? Times 52 weeks in a year. You're getting paid every week for 35 years. And so the total amount for that is $2,912,000. Okay, so that part's pretty easy. And I'm going to write it out for you. So this is the weekly amount. So the weekly pay, number of weeks in a year, and then number of years. So this is the total value of the prize, okay? Now, if the state can earn 9% on investments, how much will they need to put into an account now to cover the payment weekly for that length of time? So what they're basically saying is, does the state actually have to put $2 million in the account for whoever's winning the prize? No. They're saying that it earns 9% interest on investments. So how much do they have to put into the account so that it will grow to the amount that the prize will be over the course of that time? So let's think about the things that we know. We know R, right? That's an easy one. We know that R is 0.09. What else do we know? We know that the deposit amount is $1,600. We're going to get paid $1,600 a week. There's 52 weeks in a year, so it's going to compound 52 times because you're getting paid every week. And it's going to happen for 35 years. So N is 35. So what is the thing we don't know here? We don't know, very simply put, how much needs to be in there in the beginning, right? We don't know the initial amount. So we're going to use the payout annuity to find how much is needed into the account to pay the prize amount. And let's write that down. So use the payout annuity formula to find the amount in the account needed at the beginning to pay the prize, the full prize amount. So we're going to use the formula. Let me go ahead and copy it because I'm getting tired now. I'm not in the mood to write it out again. And you're like, thanks a lot. I'm not really in the mood either. Okay. So here we go. So there's the formula. So let's bring it on down. Okay, so there she is. So I'm going to plug in. And remember, we're solving for P sub 0. So that's the thing I'm leaving alone. So P sub 0 equals, and we're going to write D 1 minus 1 plus R over K raised to the negative 35 times 52, close, all over, and then R over K, 0.09 over K, which is 52. Okay, so now we're going to plug it in our calculator because this is nice and easy peasy from here on out. So let's go ahead and do that. So we're going to put in let me put the fraction first. There we go. 1,600. 1 minus 1 plus 0.09 divided by 52. And then raised to, so hit that A to the B button, negative 35 parentheses 52, right arrow to get out of it all, and then we're going to go underneath. And then last thing is the bottom, 0.09 divided by 52. All right, and what do we get as our final answer? We get, let me make this a little bit smaller so we can actually write it. We get as our final answer P sub 0 equals 884,722, $884,722.02. That is what needs to be in deposited account now to pay the price. If that amount is sitting in there in the beginning and we take out $1,600 a month or a week, we will get that full payout amount of the $2 million over the 35 years. Okay? All right. Whew. We are almost there, folks. A little bit left. This last example is very similar to a homework question, and it's split into two parts. In your homework, it's just going to be one question, but, if you can follow me on this, then you'll be good on that question, okay? All right, so here's the question. You want to be able to withdraw $40,000 from your account each year for 15 years after you retire. You expect to retire in 25 years. If your account earns 7% interest, how much will you need to deposit each year until retirement to achieve your achievement goal, to achieve your retirement goals? Okay, so here's what I want you to think about. I'm going to just draw down here for a second, okay? So you want to be able to retire in 25 years from now, okay? So in 25 years, I'm just giving you a little bit of a visual, okay? In 25 years, you will retire, okay? So for 25 years, we're going to save money, right? We want to save money because we're going to retire someday. So for 25 years, you save money. And then what happens after you hit that retirement? What happens on the day that you retire? Then we start to take out money, right? So you take out money. And so the part of the problem that we need to think about is you want to withdraw $40,000 each year for 15 years. So we're going to take out $40,000 per year for 15 years when we are already retired, okay? And so what they're asking is and by the way, if we haven't already made it obvious, your first part of the problem is the savings, right? You have the savings annuity. And then the second aspect is what you're going to do after retirement, which is the payout, right? That's like the payout annuity. So what's interesting about this problem is we kind of have to work backwards, right? Because we want to know if this is how much you want to take out per year for that length of time, what needs to be in the account in the beginning? And then once you figure out this, so if I'm going to retire in 25 years, I need to save X amount per year for 25 years. So one more time, what you're going to do is you're going to start off by saying, I need money. For the next 15 years, I want to take out this much. Okay, so if that's how much you want to take out, what is the amount that needs to be in the account on the day that you retire? After you figure that out, now you can make your plan. If I want to have that much in my account, how much do I have to save between now and then? So that's kind of the plan for this problem. It's two parts, and you're kind of working backwards. You have to start off by saying, this is what I want to do. This is how much needs to be in there. And then this is how I'm going to save for it. Okay? So let's look up here. You want to withdraw $40,000 per year for 15 years. So we need to figure out how much is in the retirement account on day one of retirement, which is what we just said. So we're going to use the payout formula and figure out what is the thing that needs to be in there at the beginning, meaning the initial amount, right? Because in the payout formula, it's what's in there at the beginning. What needs to be in there at the beginning of retirement? So what do we know? We know the payout amount, which is D. How much are we going to take out? We want to take out $40,000. We want to take it out once a year. And we want to do that for 15 years, right? So N is 15. And my K is going to be 1 because we're only taking it out once a year. And then my R is going to be my percentage as a decimal, 0.07. So what is the thing I don't know? I don't know the initial. I'm solving for the initial. So the initial amount is going to be 40,000, and you can look up at the payout formula if you need to look at it again. 40,000, 1 minus 1 plus 0.07 over 1 raised to negative 15 times 1, close, close, all over, and then 0.07 over 1. Okay, let's put that in the calculator and see what we get. This is how much needs to be in the account at the end. Sorry, I'm not a good side-by-side DJ here. Okay, so let's put that in. So we've got 40,000 parentheses 1 minus 1 plus 0.07 over 1. Yes, you don't really need to write the over 1, but I'm going to do it anyway just so everybody can see what I'm writing there and why we're doing it that way. A to the B to get that exponent. Negative 15 times 1. Yes, that's just 15, but I'm going to write it in there so that everybody knows what I'm doing. Then that whole thing goes over 0.07 over 1. All right, so what do we get as our answer? We get that the initial amount is $316,316.56. That is how much needs to be in the account on day 1 of retirement. So now that we know that number, now we need to figure out how much do we need to save every year in order to meet that requirement when we retire in 25 years. So now that P sub 0 becomes my P sub N. That's what we now want in the account at the end of our saving for 25 years. So I'm going to write that in for P sub N because that is now part of my savings annuity. So P sub N is that. N is going to be for 25 years of hard-earned saving. R is going to still be my 0.07. My K is still going to be 1 because we're only saving once a year. Yes, this is a little weird because most of the time people don't save once a year. They save maybe once a month or maybe even once every paycheck. So maybe this is not what you would do, but for this problem, it is K being 1. So we're going to use the savings annuity formula, and P sub N is going to be 364,000. What is the thing that we don't know? I'm going to write it over here. The thing we don't know is D. How much do you have to save every single month? So we're going to use the savings annuity formula. So we're going to put in P sub N, 316.56 equals P sub N equals, and we're solving for D, so parentheses D, parentheses, 1 plus 0.07 over 1, close, 25 times 1, minus 1, close, close, all over, and then 0.07 over 1. As we've done several times, if I'm solving for D, I can take all of this and divide it. So I'm going to do that. So let's go ahead and write that in. So 364,316.56 all goes over, and then I'm literally going to type all of that stuff in the brackets. So that's going to be parentheses, parentheses, 1 plus 0.07 over 1 raised to 25 times 1. I know that this is a little repetitive to write these ones that you don't really need, but what if it wasn't 1, you know? Like, what if it was, oh, by the way, yeah, you can't type a times in the exponent. You have to use a parenthesis. What if it wasn't 1, you know? Like, you would want to see that. So I'm just writing it just because this is what you'll always do. And then right arrow to get out of the exponent, minus 1, okay? Then on the bottom, 0.07 goes over 1. Okay, so what do we need to save once a year for the next 25 years so that we'll have $364,316 and 56 cents on the day that we retire? We need to save $5,760.03 every year. So $5,000 needs to get put away once a year. Now, you might be asking yourself, why would you put it away once a year, right? Why would we put it away once a year? And that is a great question. Many individuals do not put it away once a year. They put it away monthly, weekly, you get the point. So that is, food for thought, but this is how you do this problem. So when you see this in your homework, remember, it's a work backwards problem. Figure out with the payout formula first what needs to be in the account when you retire, and then after you figure that out, then you use your savings annuity to figure out how much you need to save per however many increments for that length of time, and then that will give you your final answer. So there you go. All right, well, I hope this video has been helpful. I know that the calculator situation for this unit is a little bit sticky, so I hope that I was clear enough on how to type some of these ones up top, like over here, into your calculators. Of course, if you have any sort of issue putting these in, please reach out to your instructor, and you will definitely be able to get more assistance on typing it in the calculator. All right, have a wonderful, I know I'm scrolling here as I want to make sure I looked at everything. But yeah, so hopefully this was clear for y'all, and if you have any other questions, please let us know. I hope this was helpful. Enjoy the rest of your